Welcome to Data Skeptic. Our mini episodes are gentle introductions to concepts related to artificial intelligence. These short discussions are meant to serve as a primer for the topic. Learn more by reading our show notes at dataskeptic.com.
Yeah, so what we were talking about is this framework for studying multi-agent systems. So there's every MDP, Markov Decision Process, has a tuple of four things: the states, the actions, the transition function that describes how the state evolves, and then the reward function, which describes what sort of reward the agent gets. And this is a very general framework for describing most games or interactions.
Oh yes, I vaguely remember. This is vocabulary specific to this Markov thing.
Yeah. So that's the MDP. Now there's a generalization of that called the POMDP, which stands for the Partially Observable Markov Decision Process, the key thing being the partially observability thing.
I assume it means you could only have insight into parts of it.
You pretty much nailed it, but tell me specifically a little more what you're thinking.
Sounds like it's a formula for saying, hey, if you could only have insight into these few things, then your guess accuracy could increase if you use my rules or formula.
Oh, interesting. So I could see where you would think that. It's not that that's not what we're talking about here, but it's a little astray. So I'm going to rope you back in more and say that you kind of had it on the first try, where in a game, you can't now perceive everything. So chess, on the one hand, is fully observable. You can always see every piece on the board. There's no secrets, right?
The secret is, what is the player going to do next?
Yeah, but the whole state of the game can be observed. We can't observe what action they're going to take in the future, but we can observe the whole state, and so can they. Mm-hmm. But compare that to a game like Battleship, right? What happens there?
Oh, well, it's hidden. Also, people can lie. Remember James, our brother-in-law? He said he would play it with his brothers, and then he was really competitive. They were like, A4, and that was his ship. He would just move his ship over and be like, nope. I never thought about lying. I mean, I thought about it, but I didn't do it just because I guess I didn't care enough.
Well, we could do another episode on the optimal ways to lie, how a Bayesian would, say your ship is elsewhere and then keep track of the least likely positions it could be in or something. But no, in fact, today we're talking just about the partial observability. So in Battleship, you see your own pieces, right? Mm-hmm. And hopefully they stay in the same place. Those are the rules.
If you're not lying,
right?
Yep.
And then you don't see the opponent's pieces. However, what can you do?
You could move yours to lie.
No, stop with the cheating. What's the normal operation of the game?
Okay, so I think Battleship got its start from either World War I or II. I don't know who. But you have to nail the ship. Its exact coordinates.
What is the action you take in this game?
You just say A4, and then you just guess on the grid where you think it is.
Yeah, you announce a position, a row, and a column. So your action space is rows times columns, basically. Pretty big action space.
The opponent will say, I assume they say yes or no.
And hopefully, let's just trust that the opponent is actually playing the game without cheating. Then you would get a signal back, true or false. What happens now in your mind when you get that observation?
Oh, well, you have these little pegs. So you put them on your board and you keep track of which ones were no's.
Would you feel comfortable with it if I said those pegs represent your beliefs?
Sure. They're your guesses, which are your beliefs. But is a guess a belief? Or is it just a strategy?
The result, when you put the peg, you're saying, I already put a bomb here and it was not a hit, right? Or maybe it was a hit. You have two colored pegs, right?
Yeah.
When you put the peg in, you say, I now believe that the state at this grid point is occupied or not.
You could only assume that your opponent is telling the truth.
Yeah, I call it your beliefs because essentially that's you trying to record information you now know about the state. Although actually you want to encode your beliefs in a little bit smarter of a way, because the beliefs in the straightforward version of the game, each space can be empty or, red or blue then, whatever the colors are. So you have three options. But actually you'd know a little bit more than that when you update your beliefs. For example, if you get a hit and it's your first hit in the game, then you know with certainty that the smallest ship is 2 units. Then you know once you got a hit, one of the neighboring cells has to be a hit.
Yeah.
Your beliefs need to be updated in a more clever way than the game kind of allows you to. But if you solve the game with a POMDP, maybe you can find an optimal solution. And so I talked about Battleship to establish this partial observability thing. We can think of it much more generally, right? Like, in your life, you can't observe, if you're negotiating something, you don't know the private information of the seller and All right, so let's get on to the classic example in POMDPs. This is the one people use to teach it. It's called the Lady and the Tiger game. So here's the game. You are standing before two doors. Behind one door is a prize for which you are given 10 points if you open the correct door. Behind the other door is a penalty where you get minus 100 you have to pay. You get to pick which door you want, but you can only open one door.
Okay, so behind the door is a prize.
Yeah.
And one of the doors is a tiger.
Yeah.
Can I go up to the door and put my ear on the door? Because I would say with 100% accuracy, if I put my ear to the door.
Yeah, so that's not allowed in the game. You have to stand behind the line, this line right here.
There's a line?
Yeah, see right here, there's a line. And you stand behind it, and you get to listen. Now, we've already established your hearing. How would you describe it? Is it good?
It's average.
It's average. So let's say you have about an 85% probability of hearing the correct location of the growl from the tiger. You can't perfectly reliably hear the tiger. You might hear the growl come from the left, but our ears aren't perfect. 15% of the time, you'll think it's the left door and it's the right, or vice versa.
Okay.
All right. Here's where the game gets a little tricky. You can listen as long as you want, and listening is a discrete event. So you can listen, hear a growl, choose to listen again, hear another growl. Now, if you did that, maybe you would hear like two growls from the left, and that would be maybe consistent evidence that the tiger's on the left. Every time you want to listen, you pay $1. And as soon as you think you know where the tiger is, then you flip to the other door because you want to find the prize where the tiger is not, and then you open that door. If it's there, you get 10 points. If it's a tiger, it bites your hand and you get minus 100. All right? You got the mechanics of the game?
How long is a listen?
Like 1 second. It's a discrete event, so think more
then
like a video game.
How do we know if it's going to growl during that 1 second?
Oh, it's guaranteed to growl. The tiger is constantly growling. It's a very angry tiger.
Okay.
How would you go about playing this game?
I mean, obviously, let's just start. You could just start and go, okay, let's pay for one listen.
Yeah, okay. And what if you hear a growl on the right?
Well, you might go, how sure am I? Should I just chance it or not?
Yeah, that's the question.
Me, I'm a safe person. I will at least have 2 listens.
What if they contradict each other?
Oh, well, then I'd have a third. If I wasn't sure. After 2 listens, I wasn't sure I'd have a third.
Interesting. Let's go back to 0. This time, you're just starting to play the game. You hear 2 growls on the right in a row. Now what do?
I'd probably just go ahead and see what happens.
You open the other door?
Yeah.
Really?
Yeah.
Oh, because that's the right answer.
Oh.
Yeah, the optimal answer with the reward function I described is 2 consistent listens, contingent upon all those details I gave you. You start listening, and you can kind of keep a counter, basically. So if you hear, a growl from the right, that's +1, growl from the left, -1. Contradictory evidence cancels itself out because your hearing is symmetrical. In my definition, it's 85% reliable either way. So 2 inconsistent measurements cancel each other out. But if you hear 2 in a row, that puts your belief high enough, statistically speaking, based on all this data, that the utility you get from opening the door is higher than what you'd get from listening more consistently. So you could become more confident, but it's just not worth the wait, basically.
Yeah, that was actually my logic. My logic is I'm just going to learn more about playing the game rather than listening. So I was like, let's say the tiger was behind the door. Well, I'd sure learn fast, right? I would be like, whoa, wrong mistake.
Oh, I forgot to tell you a rule. Once you open a door, the game resets. And the tiger has a 50-50 chance of switching positions.
Yeah, I know. But that encourages me to learn from that experience a bad decision.
Yeah.
So I would learn faster that way rather than just listen for 10 times.
Oh, so you're looking to employ reinforcement learning, basically.
I'm just going to learn faster. I just know if you open the door with the damn tiger, you're going to be like, no. And then you're going to be like, okay. Really have to listen next time. Then I'd probably do some meditation practices before. I'd be like, okay, now I'm ready for my listen.
Yeah. So when I just asserted to you that the optimal policy is to wait for 2 consistent growls and then open the other door, that is a very, very overly summarized version of this. I didn't tell you anything about how you arrive at that solution, right?
Okay, well, how?
Through the process of solving a POMDP. Computing the policy of a POMDP, as you've been hearing about, involves learning and problem solving. A POMDP doesn't just value the immediate reward it gets, but it also looks for long-term reward. Sometimes it will select actions that are less appealing in the short term if it finds that in doing so it learns something that it finds valuable for the future. In other words, learning is a very active task. You have to seek it out and engage in challenging problems to learn effectively. A great place to do that is at brilliant.org. They've got a variety of courses for you to check out. Start with probability or linear algebra if you don't know where else to begin. One of the things I found special about Brilliant is how it helps you learn by doing. The courses are filled with challenging problems that reinforce the concepts you just read about. It's interactive and you get feedback about how well you're doing. Brilliant feels more like fun than a course to me, and it's got excellent features for tracking your progress. If you're a lifelong learner looking for a great resource, head over to brilliant.org/dataskeptics and review all of the interactive options they've got available in comp sci, math, and science. You're not going to run out of challenging problems. Head over to brilliant.org/dataskeptics.
Okay, well, how?
Through the process of solving a POMDP. So you use something called value iteration, where essentially you consider all paths, but there's some dynamic programming involved where you prune certain things down. And it's very computationally expensive. Like we've talked about, it suffers from the curse of dimensionality.
Why does it take so long?
Because in the process of computing, it follows something called the Bellman equation. And the Bellman equation, while it's optimized in a certain way, it's very brute force. It kind of says, find me the action which is most optimal for my current belief state. And then as you take actions, you get new information, right? New growls, which help you update your beliefs and know with more certainty where the tiger is, which then opens up new opportunities, because then you say, well, what are my optimal actions if I have this belief state? So you have to kind of compute across all possible belief states, and that is a massive exploration, a lot of recursive stuff going on.
So what was the answer?
The answer, out pops a policy. So that policy, which can be described by a finite state machine actually, it basically says start listening and keep a tally. If you hear a consistent growl, make a tally mark. And if you hear an inconsistent one, take away a tally mark. And as soon as you accumulate 2 tallies either way, then you're confident enough about the location of the tiger, so you open the other door, then the game resets and you do the same procedure again.
So you're saying your calculation on that slow computer meant it calculated all these possibilities and then told you some kind of rule that was optimal?
It was able to compress that whole massive exploration into this very simple policy that any simple computer could run, no problem.
But how many times did it do it?
What do you mean by times?
I mean, did it run through a scenario A, scenario B, or?
Yeah, it starts from the initial belief state, and then it tries to evolve that. It kind of asks a lot of what-if questions, like, okay, well, I could go and open the door right away. What happens if I do that? And the answer is, well, 50% chance, given what I know right now, that I have to pay the penalty, and a 50% chance I get the reward. Now, the penalty is so much bigger that I can see right away, if I only have one round to play, I do not want to open a door. It's not worth it. I'll just take the -1 for listening. And even in 2 rounds, I just want to listen, get out of there. But if I play it for 3 rounds, then I should listen, and maybe if I learn where they are, then I can get that $10 prize. But if maybe I listen, and it's inconsistent, I got to stay conservative.
So it's thinking of all these different scenarios.
Yep.
How do you train it to think of that?
You don't, exactly. You describe the whole game very meticulously. What the states are, what the actions are, how the state transitions based on, its own sort of nature and also any actions you take that alter it. What rewards you get, how you get the points in this game, and the observation function. So how likely you are to hear different things in different scenarios, just the sort of precision of your sensors.
So how do you remember all these states to input? Is there a program that has a template and asks you these input fields?
Oh, that would be a great program if someone wants to write that. I've toyed around with doing an updated version of this solver because I have a clever way I could solve it with distributed computing, actually, in a slight approximation of the belief space. But I haven't done that yet, and there aren't a lot of great tools out there for solving POMDPs. I think it pretty much goes back to like the Cassandra problem solver.
You just have to know.
Yeah, and it has kind of like a file format, so you just encode your problem in its format.
Okay.
Now, here's an interesting thing. Even though you kind of spoiled this episode by guessing immediately what the optimal solution was.
That was not guessing. I am a smart person, and that is how I make logical decisions. I'm like a data science computer.
Yeah, well, let's see. I don't know if you had adequate time on your bounded resources to have computed the optimal solution.
I don't need to. I have however old years experience I have.
Oh, experience.
From making many decisions.
And you applied transfer learning, I see.
I don't know what that is, but yeah, sure.
Okay. So maybe that's how you got the correct strategy so quickly.
I'm elderly and wise.
All right. Well, let me do this. What if instead of 85% accurate hearing, you had 99% accurate hearing? How does the game change then?
Well, then the first time I hear it, I'd make a decision.
You're right. What if you had 65% hearing?
I would definitely need 2 chances.
Well, obviously, because you need at least the same as 85. Do you need more?
Let's see now. 2 chances. That's not that great. I guess I need 3 listens.
I believe the answer's 4, but I haven't worked that out in over a decade. It's been a long time since I looked at that. The point is, though, that even as long as your hearing is above 50%, you can always do something with it. You just need more and more observations because you're going to have a lot more noise in the data. And so POMDPs are really great. My favorite application, the only time I've ever been able to do something cool in the real world with them, is a small industrial scale project where we had all this sensor data from valves and stuff, and what the pressure was coming in, and that had to do an actuator and control this one pipe thing. So the action was where we put the pipes, the control setting, and all the sensor data were the inputs. So we were able to learn optimal policies for that because it was a very confined problem. And it was cool because we also knew the accuracies of all the sensors, so we could code them in. It was perfect for a POMDP. Now, I've been praising POMDPs all day, and for good reason. They're this very universal tool for describing a problem. And if yours fits this framework, which Partial Observable Games is a very general framework, the catch would be if you know all these things like the observation function, the transition function. But if you can encode a POMDP, it's suffering from the curse of dimensionality here. So in order to get around that and solve real-world problems outside of just sort of toy problems that often are the staples for POMDPs, what a lot of people are doing to try and make these techniques more useful is to find approximations. For example, in a POMDP, you kind of always hold on to any grain of truth or glimmer of hope. So even if you hear 1,000 times in a row a growl from the left, most people would be convinced the tiger's on the left. But a POMDP will say no, with some very, very, very tiny probability, we're still going to consider the possibility that our sensor was just super unlucky. And that's the state of the world. When actually probably if it's, a 1 in a billion chance that you were just unlucky, you can forget about that scenario, right? And throw it away. Mm-hmm. So approximations like that of the belief space can make these problems a little more possible. And there's lots of interesting variants. People are using deep learning now to try and learn some of the belief space. There's even a quantum POMDPs that former guest Scott Aronson is a co-author on. There's this cool paper where they have figured out a way to use a quantum computer to get a somewhat nice gain on complexity for solving these things by basically leveraging quantum techniques to represent the belief space. So lots of cool, fun things going on with POMDPs, but they're not the most widely applicable tool simply because of the curse of dimensionality. But who knows, as different approximations come in, people find the right libraries to do this kind of stuff, well, maybe we'll see a nice resurgence of this really interesting and useful tool in the AI space. Anyway, thanks as always for joining me, Linda.
Well, thank you.
Good night.
Good night. Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.